How you doing? I'm Mr. Rose, and today we're going to talk, or continue to talk, a little bit about electric forces. Here, again, it's doing things on the cheap, so it's hard to find the camera. I'd like you to give this a read, pause the video, and write down all your given information. As always, I would like you to attempt to solve this problem before you try and watch me solve this problem. That being said, I did start out by just putting my givens on the board to try and make it less back and forth. I put a y and then x-axis. I have my 4 points, Q1, Q2, Q3, Q4. They're separated, 1 and 3 are separated by distance A, 1 and 2 are separated by distance A, which implies this is obviously a square, so everything is nice and even. That also means at some point I'm going to need to find, if I need to find the angle between 1 and 4 and or 2 and 3, that should be something that's nice and easy. Also, given my parameters, Q1 and Q4 equal, and that's a big Q, Q2 and Q3 equal, and that's a little q, I'm looking for the ratio of big Q to little q if the force on 1 and or the force on 3, the net force acting on those guys, equals 0. So, to do that, the first thing I did is I started by redrawing my picture because, this was in a textbook or something. I'm redrawing my picture. And now I'm going to start analyzing that picture. And recall, I would always say the first step is to draw a free body diagram of the objects I'm looking at. So I'm looking at object either 1 or object 3. That's my goal, right? I want to know what are the forces, what is my ratio if the net force on those two things is equal to 0. Well, if I start thinking about charges and forces, I know that forces on charges either push or pull. In order to have a net force of this guy acting on 0, that means I need some pull that way, I need some pull that way, and or some push that way, and some push that way, and then whatever the opposite is, the opposite needs to come from Q2. So, since those guys are the same, right, Q2 and Q3 equal to each other, Q2, Q3 equal to each other, that means those are the same charge. So I'm going to get a force pushing that thing away. That also implies that those two have to be the opposite charge. So I'm going to draw a free body diagram. First I'm going to draw on Q3. Trying to write Q3, there you go. I'm going to draw my free body diagram on Q3. I know the force of 2 and 3, the force of 3, the force on 3 from 2. So that is the force of 2 on 3 is pushing it away, because those are the same charges. Now, I've got force 1, 3, and force 4, 3. Those have to be opposite charge. This is the force of 1 on 3. And that is the force of 4 on 3. So hopefully you can see what I have here. I wrote FO3, 103. That would be my free body diagram. And by inspection, since the net force is 0, I know this has to equal that plus that. I can do the same thing for where you're looking for F1, or Q1 rather. So I'll draw my Q1 here. That's my Q1. And we've got the same kind of concept. I know the force of 1 and 4. Those guys obviously have to repel. I'm going that direction. Force of 4 on 1. And then 1, 3 have to attract. And, what did I say? 1, 3, and 1, 2 have to attract. So I would have a wrong color. F1 on, that should be 3 on 1, and then this would be F4 on, F2 on 1. So now I have a nice free body diagram, and it doesn't matter which one I analyze to start. I'm going to analyze this one to start because that was the one I drew first, and we have to remember two things. 1, forces obey the law of superposition. 2, I have to add vector forces as vector components. So I'm going to say I know for an absolute fact that the absolute value of F23 has to be equal to F1, 3 plus F4, 3. All right, that just makes sense. If this is 45, this is 45. 45 minus 45 is 0. That's what we're looking for. We're looking for a net force equaling to 0. So how do I start doing that? Well, couple things. Thing number one, because this is a square, it makes my job a lot easier. It's a square with two sides, so I know if this is side A, this is side A. I'll put a different color. I can throw a diagonal straight across anything. I'm looking at Q3, so I'm going to go this way. I know that's side A, so I know this has to be the square root of 2a squared. That is just Pythagorean theorem. I am, like I said, old enough that I may have helped derive Pythagorean theorem before, so that I know for a fact. Also, since it is a square, I know this force, when I break it down, I can break it down to a y component and x component. I can break that down to the y component and to the x component. And I know the angle in there is going to be, you can't see me, is going to be 45 degrees. I know that again because of a nice symmetrical argument. It's a square. Cut the square in half, you know it is 45 degrees on either side of the triangle. It makes life nice and easy for something like this. Now I'm going to do, literally, F1, 3. I'm going to do F4, 3. And then I'm going to do F2, 3. I know F1, 3. That's that guy right there. I've got a small q and a big Q, so I know F1, 3 equals 1 over 4 pi epsilon 0 times. I've got a little q. I've got a big Q. And I'm dividing that by a squared. What direction is that? F1, 3. That is also in the j hat direction. We need the direction because force is a vector. Next, I can do F4, 3. F4 on 3 is equal to, again, 1 over 4 pi epsilon 0 times, I've got the same thing here again. I've got a red and I've got a black. In other words, I've got a big Q and a little q. So I've got a Q there. I've got a Q there, divided by, again, an a squared. And that is my force in the positive I hat direction. So I've got the force in the positive y, I've got the force in the positive x. And now if I look at the components that I have here, it makes sense that I've got a negative to cancel that out, and I've got the negative to cancel that out. That's perfect. So now I'm going to do F2, 3. F2, 3 is going to be 1 over 4 pi epsilon 0 times. I've got an I hat and a j hat component, or a sine and a cosine of 45 degrees. I know it is F2, 3 is because of the same charge. So I'm going to have Q and Q, two small Q's on the top. I'm on the wrong side. I'm going to have two small Q's on the top. I'm going to have over the square root of 2a squared. Whole thing squared, since it's over an r squared. So this is just going to be over 2a squared. I can just drop that squared right out there. But now I need, well, what do? Am I doing the I hat or the j hat? Well, I'm going to do I first because that makes sense. So that should be the cosine of 45 degrees. In the I hat direction. And then we can clearly see from symmetry, you can't see me over on the board over here. I'm going to do the same thing. Actually, I'll come back to that in the end. I'm going to say plus 1 over 4 pi epsilon 0 times Q1, get rid of the Q1 and Q2, Q over 2a squared times the sine of 45 in the j hat direction. Man, that is all squeezed in there. And you can see me, but you can hear me. That is all squeezed in there. Now, I did drop something. Think to yourself, what did Mr. Rose drop? Mr. Rose dropped directions. This is in the negative direction. This is in the negative direction. Look at my diagram. Definitely in the negative direction. So this should be negative out there plus the negative over there. You can see I've got a common factor. So I'm going to say F23, pull that out, negative 1 over 4 pi epsilon 0 times Q over 2a squared cosine 45 I hat plus Q over 2a squared sine 45 j hat. Whew. So now I've got my x component, my y, actually that's my y component, my x component of that part. I've got F23, and next thing I can do is basically set them equal to each other. I'm going to pause and erase some stuff. Okay, I decided not to erase some stuff. I think I can fit everything in here, which is what I just quarantined off. So, two things. As I was going, I realized I pulled this out. I'm not going to go back and pull it back in, but since I'm in the I hat and the j hat, when I combine components, it's better to not pull that out. So don't worry about that here. This is my general formula. But I'm going to go back to comparing my components because I need the x direction, or the I hat component, and the y direction, the j hat component, which I have here and here, and I've got that factor here. So if I'm looking at F net, right, F net in the x direction, F net in the x direction has got to be my I hat component here and my I hat component here. So I would say it is 1 over 4 pi epsilon 0 times little q, big Q, over a squared. That's in my I hat component. Plus this in my I hat component. Negative 1 over 4 pi epsilon 0 times Q over 2a squared times the cosine of 45. That's in my, I threw that extra parentheses, that's in my I hat component. We can see that cancels out. So now I have in the x direction, fx equals q over a squared plus little q over 2a squared. We know that whole thing, my net force, must equal 0. Thus, I know q times q over a squared equals little q times little q over 2 times a squared. Oh, I dropped my cosine 45 degrees. We should know the cosine of 45 degrees is, pause for effect, square root of 2. So I have, let me throw that over here, sorry, equals 0 times the square root of 2 times the square root of 2. That gets rid of my cosine. And now what do? I can start canceling out the things that I know. I get rid of that. I get rid of that. I can get rid of one of those. I can get rid of one of those. And what do I have left? I've got a big Q equals a little q times the square root of 2 over 2. So we end up with the ratio of Q over Q is the square root of 2 over 2.